In this recording, we'll define some types of energy that are used quite often in dealing with motion. First, let's start with kinetic energy, or the energy associated with motion. Remember, the word kinetic means motion. By definition, kinetic energy is just 1/2 of mv squared. Okay, I'm using the symbol E sub k, E for energy and K for kinetic, and it is 1/2. M would be the mass of the object we are talking about, and V is its velocity. Remember, energy, like work, they are scalars. Notice also it's V squared, so the kinetic energy is going to depend drastically on the velocity of the object. Now, if an object is not moving, it's going to have no kinetic energy. You cannot have a negative kinetic energy. You see from this expression, it's positive. But then also, if you think of it, you have that motion or you don't. There is no having a negative motion. We are talking about energy. So you have kinetic energy or you don't. Now, the unit for the kinetic energy is mass, that's kilogram, times meter per second, that is squared. Now, if you remember, kilogram times meters per second squared, that's newtons, MA, and then times meter, which is newtons times meter, which is joules, which makes sense. All energies and work should have the unit of joules, as we have here. Now, another quantity that's very important in the study of motion is what we call potential energy. The word potential is the key word here when we talk of potential energy. Something that has the ability of doing work. It is, in other words, energy that is stored. Now, there are different types of potential energy. For example, there is chemical potential energy, electrical potential energy. A chemical potential energy is like, for example, what you have in an apple before you eat it. We'll talk mainly of two types of potential energy when we talk about motion. One of them is the one associated with gravity, what we call the gravitational potential energy. It is associated with height. This is the kind of energy that we rely on in getting electricity out of hydroelectric power plants. In that case, what we do, we have water that's at a higher level than other water, and we make that water lose that gravitational potential energy that it has due to that height difference, and convert that gravitational potential energy into kinetic energy, and then with that increased kinetic energy, having that water collide with a turbine, rotate the turbine, and produce for us electricity, and the process electrical energy. Now, what we define as gravitational potential energy, so height is quite important, is m, the mass of the object, g, the gravitational field, times h, the height. How high is the object is. How high the object is. Now, there are key important points here. We talk about gravitational potential energy. By the way, there are other definitions of gravitational potential energy that are more general, but this is expression for gravitational potential energy at the surface of a planet. Well, I'm not sure if we'll talk about the other one in this course or not, but this is the expression that we use at the surface of a planet when we deal with motion at the surface of a planet. Now, if we are going to deal with objects that are going to move from the surface of a planet to outer space, then we know that small g is going to change then, so this equation is not going to work anymore. Now, h is going to be measured relative to a reference point. Now, if I have something here relative to ground, let's say it is 1 meter above ground and it has a mass of 1 kilogram, So now its gravitational potential energy relative to ground is going to be 1 kilogram times 10 meters per second squared times 1. So it's going to be 10 joules. Now, what's important is how far it is above ground, vertically. It does not depend on anything along the horizontal, vertical height. For example, if my mass was actually along an incline, that's still the case. Its gravitational potential energy relative to ground level is still 10 joules. Now, that same object, I could calculate its gravitational potential energy relative to another reference point. Let's say second floor building somewhere here, which is 2 meters above there. Then the gravitational potential energy is going to be minus 20 joules. It's going to be minus 2 for H, G 10, and 1. So it's minus 20 joules. So even though we have quite different numbers, they are both correct because both of them are expressed relative to a particular reference point. And that's not going to change the results in terms of conservation of energy and so on later on. Because what's going to matter from what we are going to see later on is not a gravitational potential energy. What's going to matter more is the change in gravitational potential energy. How much of the gravitational potential energy are you going to change into something else? Or how much of that other type of energy are you going to change in gravitational potential energy? That's what's going to be important. Now, another type of potential energy that's important is what we call the spring potential energy. Whenever you compress a spring, you store energy in it. Now, that spring potential energy is given by 1/2 of K, the spring constant, times the amount by which you either stretch or compress the spring, x squared. X is measured relative to the equilibrium position, and it can be either a compression or stretching. It does not matter. It's 1/2 of kx squared. That's another type of potential energy that we'll deal with. Now, the last type of energy that we deal with is what we are going to call mechanical energy. It's a simple definition. It is the sum of the kinetic energy and potential energy of our system. Now, you notice here, I didn't say gravitational potential energy. I said just potential energy. I didn't say kinetic energy. Okay, actually, let me be precise here. We are going to see later that when an object, for example, moves and also rotates at the same time, it's going to have two kinetic energies associated with it. So all of them are going to be included here, all types of kinetic energy and all types of potential energy. When we say EP here, that can be gravitational potential energy plus spring potential energy. Whatever is relevant for that case, whatever is applicable, you need to use it. Whatever is applicable in terms of kinetic energy, you are going to use it. And the mechanical energy is the sum of all kinetic energies and all potential energies. That's what we call mechanical energy. Now, what's the importance of mechanical energy? Is the law of conservation of energy. We know that the law of conservation of energy says that energy can change form, it can be transferred, but it cannot be created or destroyed. Total energy does not change with time. Now, total energy is a general term. It involves all types of energy, making it quite complex. To account for total energy, it becomes very intricate, especially in dealing with motion. The situation can become quite difficult and quite tricky. So we limit ourselves, instead of talking about total energy, we limit ourselves to the energies that are quite relevant to motion, particularly the energies that we just talked about, or in general mechanical energy. Okay, so instead of dealing in general with the conservation of energy, we are going to deal with the conservation of mechanical energy. Now, what does the conservation of mechanical energy say? The mechanical energy is going to stay unchanged unless we have non-conservative forces, meaning lossy forces. Like if we have friction, if we have air resistance, those are going to affect the mechanical energy. Without those, the mechanical energy of our system is going to remain unchanged, meaning that the sum of the kinetic energies and potential energies at any final state is going to be the sum of these kinetic energies and potential energies at any initial state or any state in between. That sum is going to remain constant. That's what we mean by conservation of mechanical energy. And that's what we are going to work with when we use conservation of energy.